You know, in our digital world, everything is just data. A photo, a contract, a message, it can all be copied perfectly, over and over, with just a click. So how do we trust anything? How do we know if something is the real deal, or just another copy? Well, let's get into it, because the solution is one of the most clever and powerful ideas in all of technology.
So yeah, that's the big question, right? If you get sent a digital contract, how can you be absolutely sure it's the exact one the other person sent, that not even a single comma was changed along the way? And, just as important, how can you prove who really sent it? The answer, it turns out, is to create a unique, unforgeable fingerprint for that data.
To really wrap our heads around this, we need to meet the first hero of our story, the cryptographic hash function. This is the engine, the machine, that creates these amazing digital fingerprints.
Okay, that sounds super technical, I know. Mathematical algorithm, fixed length string, but honestly, the core idea is way more intuitive than it sounds. You just have to think about it in a different way.
Yep, a blender. Seriously, let's just forget about all the complex math for a second and just picture a very special, very powerful blender.
So, the document you want to fingerprint, that's your input. Those are the ingredients you're tossing into the blender. The hash function itself, that's the blender. And the output, which we call a hash, is like a perfectly mixed, one-of-a-kind smoothie. But here's the real magic of this thing. If you change the input even just a tiny, tiny bit, add one single character to your document, you get a completely different smoothie. That extreme sensitivity is everything.
Now, for this whole digital fingerprint idea to actually be secure and something we can trust, it has to follow 3 really strict rules. These rules are what give it all its power.
First, it's deterministic. This just means the same ingredients will always make the exact same smoothie, every single time. Second, it's a one-way street. If I show you the smoothie, there's no way you can work backward to figure out the original ingredients. You can't unblend it. And finally, it's collision resistant. This is a big one. It's basically impossible for 2 different sets of ingredients to somehow create the exact same smoothie.
And this brings up a really common point of confusion. Hashing is not the same as encryption. Think of encryption as a two-way street. You scramble information to keep it secret, but someone with the right key can always unscramble it. Hashing is a one-way street. The goal isn't to hide information, it's to verify its integrity. It's all about creating that unique fingerprint to prove nothing's changed.
Okay, I know this might still feel a little abstract, but I guarantee you rely on this technology every single day, probably without even thinking about it. Let's look at a couple of quick examples.
Every time you log into a secure website, this is exactly what's going on. The site never, ever stores your actual password. Can you imagine how risky that would be? Instead, it stores the hash of your password. When you log in again, it just puts the password you typed into the blender and checks if the new smoothie matches the one it has on file.
And this is so important. It means that even if hackers manage to steal that website's entire user database, they don't get your password. They just get a huge list of hashes. And because hashing is a one-way street, they can't turn those hashes back into your actual password.
Here's another one you've probably seen. Ever been downloading some software and you see this long, random-looking string of letters and numbers called a SHA-256 checksum? Guess what? That's the hash. It's the file's official fingerprint. You can download the file, run it through a hash calculator on your own computer, and if your result matches the one on the website, you have mathematical proof that the file is legit and hasn't been messed with.
All right, so hashes are fantastic for verifying that a file hasn't changed. But what about proving who it came from? For that, we need to level up. We combine our blender with another really cool idea called public key cryptography. In this system, everybody gets a pair of special linked keys, a public key that you can share with the whole world, and a private key that you keep totally secret. When you mix these keys with a hash, you get a digital signature.
It's really the best way to think about it. A digital signature is just the high-tech, mathematical version of a handwritten signature on a contract. It proves you're the one who signed off on it and that the document is exactly as you left it.
So here's how you make one. First, you take your document and create its unique hash, its fingerprint. Then, and this is the really clever part, you use your secret private key to encrypt just the hash, not the whole document, just the tiny fingerprint. That locked up hash, that's your digital signature.
So, now someone receives your document. How do they check it? Well, they take your public key, the one you share with everyone, and use it to try and unlock the signature. If it works, it reveals the original hash you created. Then, they take the document you sent and calculate a fresh hash from it themselves. If those 2 hashes are a perfect match, boom, verification. And when that match happens, you get 3 incredible, rock-solid guarantees. First, integrity. You know the document wasn't changed because the fingerprints match. Second, authenticity. You know the real sender signed it because only their secret private key could have created a signature that their public key can unlock. And third, non-repudiation. The sender can't turn around later and say, "I never sent that." The math proves they did.
Okay, so we have digital fingerprints and digital signatures. So what? Why does this all matter so much right now? Well, because when you put these two tools together, you get the absolute foundation for one of the biggest technologies out there, blockchain.
And it is no exaggeration to say that without them, things like Bitcoin or other cryptocurrencies just couldn't exist. They are the magic ingredient that allows a global network of complete strangers to agree on a shared history of who owns what, all without needing a bank or any central authority.
So how do they do it? Well, hashes are used to create this kind of digital chain, linking every group or block of transactions to the one that came before it. It creates a chain that is incredibly hard to break.
So let's start with block 1. Imagine it's full of transactions. All of that data gets fed into our blender, the hash function, and it spits out one single unique fingerprint for that entire block. We'll just call it hash A1B2.
Now this is where the chain part comes in. The next block, block 2, has its own set of new transactions, but critically, it also includes the hash from the block before it, A1B2. All of that info is then blended together to create a brand new fingerprint just for block 2. We'll call that one C3D4. You see, each block is now mathematically changed to the one before it.
And that is the security breakthrough. If anyone tries to go back and secretly change a transaction in block 1, the hash of that block would instantly and completely change. It wouldn't be A1B2 anymore, and that would immediately break the link to block 2, which is looking for A1B2. The break would be obvious, and it would cascade the entire chain, setting off alarm bells for everyone. This is what people mean when they say a blockchain is immutable.
So when you think about it, from securing your everyday password to making global cryptocurrencies possible, these ideas, digital fingerprints and digital signatures, have totally changed the game. They let us build trust not on the word of an institution, but on the cold, hard logic of mathematics. Which really leaves us with a pretty fascinating question to ponder for the future, doesn't it?